This is a brief overview of the DC motor system running Python. The microprocessor it will show up as an Arduino Nano RP2040, which is a Raspberry Pi based microprocessor. It's running CircuitPython, available from Adafruit. The editor shown is the Mu editor, also available from Adafruit. When you plug the device in, it will show up as a removable hard drive, and anything that's in code.py gets run on the microprocessor. There's two other files. These are the experiments we're going to be running. You could just rename these files code.py, and then it will run the code here. Or we're just going to copy and paste the contents of these two files into code.py to run them. First, we're going to do velocity step response. So a voltage of, let's take a look, it's going to have a step size of 2, and it's going to start off at 1.5 volts. It's going to go from 1.5 to 3.5. We'll copy this code, put it into code.py. As soon as this is saved, it will start running on the system. This has a terminal so that you can monitor this as it runs. You could print messages out here, but it's going to be streaming data to the computer. And the important part is just this main loop, which just does the step response and applies voltage to the motor. There's two plotting files. We want to run the plot step in velocity. It's going to plot reference versus theory. If we double click this, it's going to open up the GUI to plot. It's going to verify that our sample size is 5 milliseconds, which it is, and it's pretty accurate. That's just for verification. And then here we see the data being plotted in the yellow. It's going to have the theoretical response based on the analytical solution in magenta. And then the reference, in this case, is just a voltage. It's changing the voltage 1.5 to 3.5. That's why it's in different units. It's not really showing up. Here we can monitor, we can change the experiment in real time. For example, if I want to go to start off at 2.5 volts, as soon as I save it, it's going to update the microprocessor code, and it's running a different experiment. And it's plotting the corresponding theory from that. If I go back to 2, save it, it's going to modify the code. I can also change the theoretical response in real time by changing K and tau, or the offset from Coulomb friction. For example, if I think my steady state gain is larger and apply that, it'll change the corresponding the corresponding theoretical response. And both the theoretical response and the experimental can be changed in real time. So that's the first experiment. Next experiment is going to be PI, velocity control. So we're going to be going to a reference speed of 200 radians per second. The main control loop is going to be doing PI compensation. So we're going to copy all this code, paste it, and as soon as we save it, it's going to start running on the system. We're going to open up the plot PI code. It's going to connect to the device. It's going to verify that our sample time is being met. It should read 5 milliseconds, which it does, and it's accurate, so that's good. And then we can look at our graph. This is running PI compensator, and again, we can change this in real time. If we want to change our reference to 150 radians per second, I can see how it matches to 150. We could also change, again, our model or our gains. If we change the gains, we have to make sure we change the gains in the microprocessor and on the theoretical gains from this, but I could again change the steady state gain here for my theoretical response and see the result of that in real time. That's the quick overview of running experiments on microprocessor with Python.